Hey guys, welcome back to AlgoYogi. We are doing binary search series and our next problem in the list is find peak element. Let's visit LeetCode and give it a read. So a peak element is an element that is strictly greater than its neighbors. Left element and the right element, both of them strictly greater, not equal, strictly greater. So what we need to do, given a zero index integer array nums, find a peak element and return its index. If array contains multiple peak elements, just return any of those. So that's it. Pretty easy description. And you may imagine that at the last index could be just negative infinity or whatsoever. Like it's not really relevant, because when we are like solving a problem like that, we already considers these these constraints. These are the questions that you ask your interviewers, right? And usually we do have these in our these edge cases. Okay, let's keep going. In another words, like the element always considered to be strictly greater than a neighbor that is outside the array. So this is what they're saying. If let's say if we have like something at the end of the array which is greater than its previous element, then it's a strictly greater element, given that it does not have anything after that. So let's consider that something dropping to negative infinity. Okay, so yes, that would be our peak element if it is greater than the element before it, and that applies to the same to the first element. If that's greater than the next element, then we can imagine there's nothing before it, or maybe like the end of the array is the element before it. It's kind of imagining it's like a circular array, and I hope you are getting it. All right, so let's understand it on iPad and write the solution. And by the way, if you didn't notice this, we have to basically write the algorithm in big of log n time complexity. All right, okay. So brute force solution would be basically doing a linear search and checking if the first element is basically greater than next element, then just return first element. Honestly, that will be one of the accepted solution. Keep doing a linear search and then compare an element to its neighboring elements. If it is greater than both of them, then you return that element, and that will be a big of n time complexity solution, which is not accepted. It's we must write it in log n, which basically forces us to think what is it that can give me a big of log n time complexity, and that is our favorite algorithm, which is binary search. Binary search brings down the input size half from the previous iteration or whatsoever previous function call, and let's see how we're gonna decide how do we cut down our input size to half. Okay, so for example, let's take this the first example, which is example 1 is when we have our nums array as 1, 2, 3 and 1. So let's imagine this on number scale, right? So we got 1, 2, 3 and 4, and let's say this represent basically the height. So 1, let's say this is basically the index, by the way. This is the index and this represents the height. So we have 1, let's say 1, 2 and 3. 0 is over here. So 1 is first element is over here, so we can say, or I could just call it 0 should have been here there. So let's call it 0. So I'm gonna use this. So first element is at index 1. Yes, it's height 1 at index 0. Second element is index 1 is basically over here, and third is over here, and then fourth is right here. So if you see, this is the graph that you're seeing, and I made a mistake. I skipped this third index. So that should be over here. Okay, so now if you see what is the peak element, and you can see directly that this is our peak element. So we're going to return 2. 2 is why? Is because it's the index. That's what we need to return. We are not returning the element. That's not what they asked. They asked us to return the index of the peak element. All right. Let's say what if our last number was not 3 but 4. In that case, what will happen is our third element, basically fourth element, third index, would be over here. Let's say this was it. So it would be over here. This will be our fourth. So then our answer will be basically the last element, which is third index, third IDX, and that's what we will return. So how does binary search come in the picture? How do we decide? The way binary search runs is basically you find out the midpoint and you check basically if that's your peak element. How do you do that? Compare it with your neighboring elements. If it is greater than both of them, then just return it. You don't care about any other solutions. There might be multiple solutions, or there's just one solution. You found it, you return that, and get out of there. Get out of your interview. You passed. Okay. And then what if you don't? Then you need to decide which side you need to search, right? So how do you actually decide that? That's the tricky part. In this case, that's the tricky part, because there is no straightforward approach that makes you think, but because this particular array might not be sorted. But what you are really seeing is you can compare the mid element to basically its neighbors, and whichever side has the greater number, you basically decide to go for that side, and I guarantee that will return a solution. Why do I guarantee? Let's find out why that will give you a proper that will give you a solution. Okay. And the reason I say that is, let's say we had a monotonic array, 4, 5, 4 and 5. So what this will look like on the number scale would be, you have 1, then you have 2, then you have 3, you have 4, and then you have 5. Now if you were applying a binary search, so you will have basically left pointer and right pointer, and so what you're going to do is find out the middle, which will be 3. Now you compare 3 with both of these neighbors, and then you find out this is not greater than both of them. This is greater than 2, but it's not greater than 4. So then you compare which side has a greater neighbor. So this side has greater neighbor. So what I'm saying is we are deciding to go to this half. By the way, if this is the middle, then you decide to basically look for your peak element in the next half, and I guarantee that this should return basically your peak element. So in this case, you see that it's monotonic array, and the last element would be our answer. Even if it was not monotonic, maybe let's say this fifth was not is it fifth element? Yes, fifth element is 5 here. Maybe it wasn't 5. Let's say it was 0. Let's bring it down to 0. And even if right now, basically in this case, in this scenario, 5 is the answer, because after that drops to infinity. That's what the problem said. We went through it, and that will be our answer. But let's say if this element was a 0, this was 0, then this wouldn't exist here, and this will be something like, if this was 1, then 0 would be over here. This is the fifth element, which is 0. So now you see, if I'm going on to the greater neighbor side, I see the graph goes like this. So if I'm choosing to go this side, then this element is greater than the middle, which is over here, and this is greater than the next element. So there will be two scenarios. Either this is your answer, or it was a monotonic array, then last element is your answer, because that's how it need to be. If it's a monotonic array, then you return the last element if it keeps increasing. But if it doesn't, somewhere like it takes a drop, but then that means you were basically going up, and then suddenly came down. So then there will be a peak element, and that you will find out if you choose to go to that side. Same thing will happen if let's say in our answer, basically I'm gonna just change this element. Okay, you know what, it's just taking a lot of time. I'm gonna have another example, which would be having something like this. So let's say I have 5, then I have 4, then I have 3, then I have 2, then I have 1. Is there a peak element right now? Yes, there is. What is it? That's your 5. So you must have found the middle as 3, left and right pointer, and then you found out that this is a greater side. Then you must have explored this side and you came to the last element. You decided to return that, but what if this was something else? This was 3, then still you go to the size that is greater, and if you see that 3 might be here, 4 is over here, 3 is over here, so this 4 is greater than both of them, and then 2 basically keeps dropping down. So 3, 3, 4, and I think at this point I'm just going really fast, so just so that you know, like basically the decision is that whatever side has a greater neighbor, if the mid is not the peak element, then you go to the greater side. That's what I was trying to prove here, and that will return you the answer. Now why we have already understood why when you're basically shortening, or I would say like cutting down your input size to half. Each time you keep doing that, then you end up with the array or the element just of size 1, and then that's how you get the big of and time complexity big of log n. Okay, now we can write down the solution. I think it's pretty easy to understand, I guess, pretty easy to follow. So I will switch my view to LeetCode editor, and it looks pretty nice now. Okay, let's write down. So we're gonna have left and right pointer. That's basically the core step, and last would be num's length -1. That's making the right element pretty legit if the index starts at 0. Then we're gonna have a while loop, and we're gonna keep going until L is less than or equal to the, I keep making this mistake, typo not mistake. Yes. Okay, so let's find out middle. Mid would be left plus this is basically a nice way of finding mid to avoid the overflow, and I'm sure you've seen this around. So now let's decide which side to go. So if basically m is this is checking the bounds. If m is greater than 0 and m basically num's mid is basically smaller than num's mid plus mid -1, sorry, mid -1, that means my mid is smaller than my left neighbor. That means I need to go to the left side. So I bring my right pointer to mid -1. All right, left remains intact. I'm bringing down the entire search size to the left side. Okay, search array or nums array, bring input array actually. All right, and in another case would be elif would be if m is okay. This is just m is smaller than length nums. Okay, nums -1, because I will increment it, and let me tell you what I meant if that I'm gonna increment it. If mid nums is smaller than the next element towards right, if this is smaller, then I need to go to the right side. So if I need to go to right side, that means I will pick my left pointer from the left, wherever it was, and move it to next to the mid, and that will be basically left goes to mid +1. Okay, since if none of this happens, that means what? We already found our peak element, because if your mid is neither smaller nor basically is neither smaller than it's actually not neither. If both of these conditions fall, that means it's basically greater than both of them. Okay, otherwise one of them will run, and then it will just basically update that, and then we just return basically nums mid, and that should return our answer, because did they guarantee that it should exist? Otherwise just to be on safe side, I'm gonna just return -1. All right, so let's zoom out and run it on the examples, and I hope there is no mistakes. There is that is okay, this unindented. I think this should be good now, and it's returning, yes, we are not returning the number, we are returning the index, which will be m. We talked about it when understanding. All right, so voila, accepted. Let's write down the time complexity. Big of log n, and space complexity is basically constant. Okay, all right, let's go back to AlgoYogi, mark this solved, and see you guys later in next problem. Until then, bye bye.